Greetings. We know that when you go up in the mountains, the ambient pressure goes down because the height of the Earth's column is shorter. And we know that the boiling point is when the vapor pressure of a fluid equals the ambient pressure, and therefore the boiling point of water decreases as you go up in the mountains. And if you're up in the mountains where the boiling point of water is 95 degrees, and you want to bring it up to 100 degrees, one way to do so is to add a solute and use the concept of the boiling point elevation. So the question here is how much salt, table salt, sodium chloride, would we need to add to 1 kilogram of water to raise the boiling point to 100 degrees C? And then after we do this, we need to look and see how much salt you can dissolve. That is, how much salt creates a saturated solution, and if the amount you're trying to dissolve is possible. Okay, so first we want the boiling point equation for boiling point elevation, and we know that delta T is equal to I, the Van 't Hoff factor, times KB times M, the molality. Okay, and I represents the number of ions. If you have a non-electrolyte, it's 1, and that's why it's often omitted in this equation. But I like to keep it there all the time, just in case I have an electrolyte. Sodium chloride is an electrolyte. NaCl dissociates into Na plus Cl minus. Therefore, the value of I for an ideal solution is 2. That is, every mole of this creates 2 moles of ions. In reality, the value of I will be slightly less than 2, depending on the concentration. The greater the concentration, the lower it gets. And this is because as the ions are in solution, they start to interact with each other, and so they're not functioning as completely discrete particles. When we say they're 2, it's for a dilute solution where the sodium never interacts with this chloride, so they act as independent particles. Okay, Kb is the boiling point elevation constant, 0.5121 degrees Celsius per mole, and molality is the moles solute, which in this case is the NaCl, over kilograms of solvent. And this is a rather unique situation. We're using kilograms as like an algebraic unit and as a unit. The point here is that the mass must be expressed in the units of kilogram. Okay, now what do we want to do? We know that let's see what the delta T is. We can calculate that. We know that delta T is TF, the final temperature minus the initial. That's always what delta is. And we want to raise it to 100 degrees when it is 95. So that is 5 degrees C. We know I, that is 2. We know Kb, that's given up there in the overlay. And for molality, we know the mass of solvent. We're asking what mass of solute for 1 kilogram, okay? But we don't know the mole solute, okay? So I can rewrite this as delta T equals I Kb moles solute, the sodium chloride, per kilogram solvent. Okay, and I know everything but the mole solute. The thing is we're not asked for the mole solute. We're asked how many grams of table salt. But we can relate the mole solute to the grams by the formula weight. We know that the formula weight is equal to the grams, which is the mass. I'm going to use 2 loops in my M because I'm using molality here. And I'm just going to write parentheses gram to remind myself that this is mass per mole. And we use N, keep this neat if I can, N for mole, okay? So I can now solve for moles. I can say moles is equal to the mass, and I'm just going to put in a gram there, over the formula weight, which has the units of grams per mole. The confusion here is that I usually use an M like this for mass, okay? But because M is being used for molality, I have to distinguish this. So I'm writing the M with only 2 hoops instead of 3, okay? Now what I can do is I can substitute this into here, okay, and I have delta T is equal to I KB over kilogram solvent, okay, times N, okay? And N is the mass, whoops, I keep writing that the way I always write it, mass in the units of grams per formula weight, grams per mole. Okay, now the formula weight I can calculate from the formula for NaCl, and the formula weight for NaCl I believe is 58.45 grams per mole. Double check here. Yep, 58.45 grams per mole. Okay, now let's see. I know delta T, I know A, I know KB. I know the kilograms of salt, I know the formula weight. I'm solving for the mass. The mass is what I want, so I solve this for the mass. The mass, I'll never stop doing that. The mass of the NaCl in grams is equal to the delta T times the kg of the solvent times the formula weight of the solute, all over, I'm solving for this, IKB, which is equal to, okay, delta T is 5 degrees C. Kilogram solvent is 1 kilogram. The formula weight of the solute is 58.45 grams per mole of solute. And this is what I'm solving for, the grams of the solute, all divided by I, which is 2, and KB, which is 0.5121. 0.5121 degrees C over molal, okay? And molal is the moles solute per kilogram solvent, okay? Now my kilogram solvent cancel. My moles, reciprocal mole solute over reciprocal mole solute cancel. My degree C over degree C cancel, and my answer is grams of NaCl, the solute. And now I go out and I do my math, and I come up with 285 grams of NaCl. Okay, we can barely see that on the board. I'm almost running out of position. Now the question is, can I dissolve 285 grams of NaCl? So I could go on to the web here, and if we look up in the overlay, I'm not sure you're able to see this. I'll try and make it larger. The solubility of sodium chloride, this is the Wikipedia article on sodium chloride, is 359 grams per liter. Now this is very interesting. They have not told us what the temperature is, and we know that the solubility is a function of the temperature, but here it is, 359 grams per liter. We're going to assume that's room temperature. This is 285, so at the temperature of that, we could easily raise the boiling point of water 5 degrees, and we could probably even add some more salt. Okay, I hope that helped.